Okay, so in this video, we're going to focus on two different types of energy that we've talked about in class so far. The first one is going to be our gravitational potential energy. So the equation for gravitational potential energy, I'll show that first in a kind of backwards way, is m times g times h. So GPE over here, that just stands for our gravitational potential energy. And what it depends on is m for the mass measured in kilograms. That's just still same thing as it's always been, the amount of matter in some object. So it's related to how heavy something is. G is gravity. And to be more specific, it's an acceleration due to gravity, which if we're on Earth is 9.8 meters per second squared. Right? So if we were on the moon, this would be less. If we were on a really dense and massive planet like Jupiter, this is significantly higher. So this is mass dependent, but the most frequent one that we will use is this 9.8 meters per second squared, as long as we are on Earth for the problems of interest here. So even if this isn't something that is directly told to us, we'll assume that some problem is taking place on Earth is a safe thing to assume, and that the gravity is 9.8. And we can see as much in this simulation over here. The gravity that it has here is 9.8 meters per second squared. We could pick different ones actually. For the moon, it's only 1.6. For Jupiter, it's 24.8. And for custom, I can change it to anything we want. But I'm going to use Earth for now in this simulation over here. Now, one thing before I mention H that we can probably figure out and guess anyway. But if we go back over to this sort of this simulation that we've used in class before, notice when the potential energy is highest, right? So we know that mass is going to depend, or our potential energy, excuse me, is going to depend on mass. So if I increase the mass of this person, of this skateboarder, you'll see their potential energy increase. And conversely, if I make their mass really small, then their potential energy decreases with that. And you might have noticed already that when I change the gravity on here, like on the other part of the simulation, when I changed gravity to the moons and Jupiters, the potential energy changed also. So the stronger the gravitational pull is on whatever this big mass, whether it's a planet or a moon or anything else, the more gravity it has, or the higher mass that this large mass that we're on has, the stronger that gravitational pull will be, and the more gravitational potential energy this person, or in other cases, some object might have. And then the last thing that I wanted us to see is as this person gets higher into the air, their potential energy increases with that. So the higher they are, this potential energy is at its max. And then if I can get this timed almost perfectly, when this person is right there on the ground, or right here wherever our reference height is, you'll notice that their potential energy is very low because they're getting like closer and closer to this ground or this zero height. In later videos, I might talk about what this reference height would be, and you can see even this potential energy can go negative. For now, it's a safe assumption for a lot of the problems that we do in our class, in an intro physics class. It's safe to assume that usually this height or this definition of zero will usually be the ground. And so this sort of brings into the picture this last factor that gravitational potential energy depends on, which is height, measured in meters. Now, we could use this to calculate a potential energy. We could use this to calculate a mass. We could use it to calculate a height also. We could technically use it, theoretically use it to calculate a gravity, but usually there would be another more straightforward way to calculate gravity on a given planet or moon or any other large mass. And I might talk about that in a different video, but more practically we might calculate an object's mass, or more likely we would calculate an object's height if we're not calculating its gravitational potential energy. So let's do exactly that, just to see some examples of how we would use this in order to calculate these different things. So let's zoom out a little bit and practice some of these calculations. So let's say we want to know this person's potential energy at, let's see what their height is here. So their height measured here is 2.66 meters. You might have already seen the simulation give us the potential energy too. Let's say height is 2.66 meters. The mass of this person is 60 kilograms. And these are numbers that I'm just getting from the simulation over here. When I used this little thing, it told me what their height was there, 2.66 meters, and it tells me what their mass is right here. We'll assume, actually, we don't even need to assume, we're being told that their gravity here is 9.8, which we will assume if we're not told what that value of g is, we'll assume that we're on Earth and that this acceleration due to gravity is this 9.8 meters per second squared. And then maybe the question for us is, how much potential energy do they have? And we would just multiply each of these things. So mgh, let's take the 60 kilograms times our gravity, which is 9.8 meters per second squared, times this height of 2.66 meters. Okay, let's use my trusty Google calculator to find that. 60 times 9.8 times 2.66. And what this is telling me is that that potential energy at this height is 1564.08. And then the units for this is joules. So maybe I should have specified this J stands for joules, which is spelled Joules. It's a little confusing with my labeling in a different way here. Gravitational potential energy is what this GPE stands for, and that's just measured in J, pronounced just like regular joules, but spelled like some guy's name. Let's check this against what the simulation says. So 1564.08. Close to what they got. My guess for why this is a little different from what the simulation got is that it's possible that this height that is here, 2.66, in the simulation, how it's calculating it probably carries a lot more decimal points. That could also be true for the gravity on Earth. I think it's technically 9.81, and then there are, of course, plenty of other decimals after that. So that could account, would be my guess, for this difference between what I'm getting here and what the simulation is getting. It's just that this 2.66 is a slightly rounded number, but we're getting basically the right thing. Now let's do the opposite here. So in this case, this sample calculation that I just did, it was a pretty straightforward one because we were trying to calculate the gravitational potential energy, which this equation is already solved for. If we're trying to solve for a height, which is a pretty common thing to do if you're trying to design something, like in class we practice designing roller coasters, then designing or back calculating a height is a relatively useful thing to be able to do, and it's using the exact same equation, the same exact equation that we just did here for potential energy. So let's say that we want to know how high this skateboarder is going to be when they have, for whatever reason, and in future videos I'll talk about sort of like the reasons for some of these things, but for now I'll just go over how to calculate this. Let's say that we know that the gravitational potential energy in this other example is whatever it says here, 2317.8. Again, I'm sure that's a rounded thing, so the simulation just shows us one decimal point after this. And then we want to know if this person's mass is still 60 kilograms, our gravity is still 9.8 meters per second squared. We want to know how high up they're going to be when they achieve this potential energy, right? So that's sort of our unknown here now instead of this potential energy. And again, the reason that we're solving this in a different way, in a way that requires more algebra than last time, is just because this equation that we have up here for potential energy is already solved for potential energy. So we didn't really have to do a whole lot of rearrangement or manipulations to that equation to solve for that. because the equation as given already is. Here now, we don't have an equation that just says height equals blank, or height equals GPE divided by whatever. So we're going to have to do some work to isolate, basically, this variable inside of this equation for height. So let's see what that looks like. And first, we're just going to plug in the stuff that we know. So our potential energy is 2317.8. Right? So this is our GPE here. That is equal to the mass, 60 kilograms. And I'm going to leave these numbers unitless for now, which is not a good habit, but just to make the math part of this clearer, I'll do that. And we know the gravity is 9.8 meters per second squared. Well, might as well stay consistent and leave units out here. 9.8. And then I'm just going to leave h as our height because that's what we don't know the value of here. Okay. So now there are a lot of different ways that we could solve this, of course, and I'll show one possible way to do this, what I tend to do for myself, but I'm sure you all have a different way that you prefer calculating this, so that is totally encouraged. Always solve these in the way that occurs to you first, or not necessarily in the way that occurs to you first, but in your favorite way, the way that you find reliable and efficient for you. So I just am combining our 60 and our 9.8, and that gave 588. And now we can divide both sides of this equation because right now our h and 588 are being multiplied together. So to cancel that out, or to get rid of that and fully isolate our h, I'm just going to divide both sides by that and get whatever this is going to give us. So let's see, 2317.8 divided by 588. And it looks like this height is 3.94. I'll leave it rounded to about that, is equal to this height. So let's check to see whether or not this answer ended up being correct. Let's check the height. Let's get it in the simulation. Hey, this one was a closer match. I guess these were slightly less rounded than some of the other answers, so that height did in fact end up being 3.94 meters. So again, in the case of this gravitational potential energy equation, gravitational potential energy is the energy of position. So the amount of potential energy that something has is dependent on its position in relation to something else. And if we're looking at gravitational potential energy, that's its position in relation to some other mass. Because like we learned back in the beginning of the year, gravity is just some force exerted between two masses on each other. And we can solve for any different part of this equation, just like all of the other equations that we've seen this year. Any physics equation is not just an equation that can be used for one part of it, like our potential energy. It can be used to solve a mass, even the gravity, although not very common, or the height if we're designing something. The other kind of energy that we have here is kinetic energy. Now, kinetic energy is the energy of motion. So the faster something is moving, the more kinetic energy it has. And if something isn't moving at all, it doesn't have any kinetic energy at all. Although even I would challenge that with a microscopic view, although that brings into the picture thermal energy, which I won't talk about in this video. But the equation that we have for this is a little bit more complicated than our potential energy one is, but the way that we're going to use this is not fundamentally going to be any different from what we did with the other equation, or that we've done with any other equation, really. So our Ke here, that's our kinetic energy. M is still mass measured in kilograms, so that doesn't change at all. And then the V now, you would probably already guess, is our velocity, or some object's velocity, measured in our standard SI units of meters per second. It's important that we include this squared here. If you don't, you're definitely going to skew answers and find things that don't quite add up. But just like in our potential energy equation, we could solve this kinetic energy equation for any different piece of this equation. So just to take an example here, and I know we can see our kinetic energy there, but let's pretend that we just know the speed here, which is related to velocity, but let's say Our velocity was there, it looked like 5.16 meters per second. And again, I'm getting that number just from measuring using this little measuring tool in the simulation to find what this speed is. So let's say we know it's 5.16. The mass is still 60 kilograms for this skateboarder. And that's all we need. And then our question is, what is kinetic energy? Oof. So let's plug in the stuff that we know. Kinetic energy is equal to 1/2. And for 1/2, you'll see I'll show how I plug it into a calculator. I always recommend using decimals in our calculations just because using fractions puts ourselves at risk of possibly making some like order of operations mistakes. So I'm always going to use decimals. So I'll use 0.5 instead of that half. But 1/2 times the mass of 60 kilograms times 5.16 as our velocity, and then squared. Now, the way that I'm going to plug this into a calculator is the way that I would generally recommend doing it. So I'm going to square this 5.16 first so that I don't run into any issues again with those order of operations. If I square at the very end of all this, if I weren't careful about how I used parentheses, I would run the risk of like accidentally squaring the mass and the 1/2 also and throwing my answer off. So the way that I usually plug this into a calculator is I'll do 5.16, and then in this I like to use this little X to the Y button, squared, and then I can even hit enter there. So I'll square the velocity first, and then I'll go back and multiply by the mass, and then I'll multiply by the 1/2 or the 0.5, and that's how I'll get this kinetic energy. Right, so 798 I'll just round to 1 decimal, 0.8, because I think that's what the simulation does also. So to compare these, I'll just round to 1 decimal. And let's see what we get, or what this says. Oh, so close. They have 798.3 joules. And again, the reason that is probably different is because my guess would be that this 5.16 meters per second is rounded, and there are a lot more decimals that the simulation is carrying, and it's only showing 2 decimal points. So for our purposes and for the purposes of this simulation, that's the correct answer here. Now, if we wanted to solve for a velocity, so when we were designing roller coasters, that was something that was one of our big design constraints, is saying we know at this point in the roller coaster it would have to be moving exactly this fast to make it over a certain hill or to accomplish whatever task if we're designing some different system. So let's solve a problem where we know what the kinetic energy will need to be. So I'll let this go somewhere else. Let it go up here. And we're going to measure our kinetic energy. And let's see, it is 2043.9. So possibly we have applied energy conservation to like figure out what this kinetic energy would be, assuming that the mechanical energy is perfectly conserved, because we know how tall some object or system is at a certain point, and we know this is its kinetic energy. We know the mass of that skateboarder is still 60 kilograms. And the only question for us now is going to be what velocity must they achieve at this point in order to make this system work. Right, so now just like when we were solving for a height with our potential energy equation, we're going to have to do some rearranging here because this equation is not already solved for velocity. It doesn't say v equals blank. We have velocity squared, and it's multiplied by mass, multiplied by a half, so we're going to have to isolate the velocity because this equation is not already solved for it. That's different from this kinetic energy, which is already solved for in this equation. The equation as given is just kinetic energy equals, so we didn't have to do really any rearrangement or anything for that, but here we will. So let's plug in the stuff that we know for this equation. So 2043.9 is equal to, and then let's plug in the stuff that we know. So 1/2 times the mass of 60, and then times velocity squared. And I'm just going to leave velocity squared as v squared because we don't know what velocity is yet. Now, again, from here there are a lot of different ways that you could go through solving this, of course. I'll show one way to think about this. So I'll multiply our 1/2 and 60 first, and that should give us, I believe, 30 v squared. And if I were not sure, I could, of course, come over here and do 0.5 times 60, and that does give us 30. Bring down our energy, 2043.9, which still isn't changing. We haven't done anything with that yet. Now, right now, our v squared and 30 are being multiplied by each other, so let's divide this on both sides by 30. Those will cancel out, and let's see what that gives us over on the other side. So 2043.9 divided by 30, that gives us 68.13 equal to v squared. And now maybe I go back and check this to see if we got the right answer. And no, we did not, because our velocity, 8.25, is not the same thing as v squared. So we're missing one step here. And usually my mistakes are not planned. This one happened to be. So we need to take the square root of both sides so that this squared goes away. And then we get the actual velocity and not just the velocity squared. And when we do that, let's see if we get the same thing as the simulation. Let's take the square root of, and then I'll just plug in answer. I could plug in answer. If you use this Google calculator, you could just put click this answer button to plug in the exact same thing. I won't, though, just for the purposes of clarity. And we get 8.25. And then I'll include my units now. Since this is a velocity, those units are meters per second. And that is the velocity at this point. Let's see if that's what we get. I think, yes, 8.25 meters per second. So again, I think these height and velocity calculations are coming out with cleaner answers because these energies must be rounded a little less than the heights and velocities are thrown off a little more. But again, that is the overall sort of the method of problem solving with our potential and kinetic energies, and both of these types of energies are associated with what we would call mechanical energies, or they both make up what we would call mechanical energy, which is just sort of a specific type of total. But again, our potential energy is the energy associated with position. So the higher up something is, the more potential energy it has, the more gravitational potential energy that it has. And for kinetic energy, the faster something is moving, the more kinetic energy that it has. Both are dependent on mass, and we can see that here if I change this skateboarder's mass. You can see both energies over here changing. And when I increase their mass, both energies increase. When I decrease mass, both energies decrease. But gravity only affects gravitational potential energy, which isn't surprising given the name. And velocity only affects gravitational potential energy. So if this person were moving faster but horizontally without their height changing, only their kinetic energy would be changing.